All right, everyone, settle in. Welcome. So for today's explainer, I want you to totally forget the idea that a cell is just some microscopic blob. Instead, let's picture every single cell in your body as a bustling, high-tech city, and we're about to take a tour of what might be the most critical part of this city, its border.
So, if a cell is a city, think about this for a second. How does it protect itself? How does it control all that traffic? You've got nutrients coming in, waste going out, and you definitely want to keep unwanted visitors out, right? Well, the answer to all of that is its super sophisticated, always moving, intelligent border, the plasma membrane. Let's check out the itinerary for our tour and see how we're going to break this down.
Okay, here's our game plan. We'll start by looking at the architecture of the fluid mosaic wall. Then we'll meet the gates, guards, and workers. Those are the proteins doing all the heavy lifting. After that, we'll get into border control to understand the rules of transport. And we'll finish up with some final exam prep to make sure all this stuff really sticks with you. First up on our tour, the fluid mosaic wall. We're going to dive into its basic architecture. Now, when you think wall, don't picture some rigid, static brick wall. Oh no, this thing is flexible. It's constantly moving. It's a structure made mostly of lipids. So let's take a look at the actual building blocks. And here it is. This is the phospholipid. This is the fundamental brick of our entire city wall. You can see it's got two really distinct parts. This big, round head, and then these two long tails hanging off. It seems simple, but believe me, this structure is the key to how the whole membrane works. So this little molecule has a total split personality. Seriously. The head is hydrophilic. That literally means water-loving because it's got this polar phosphate group. But the tails are hydrophobic. They're water-fearing. They're just long fatty acid chains, and they want nothing to do with water. We call this dual nature amphipathic, and it's absolutely crucial. So, what do you think happens when you dump millions of these little guys into the watery environment inside and outside a cell? Well, something amazing happens. They automatically assemble themselves. It's all about minimizing energy. The water-fearing tails frantically hide from the water, turning inwards to face each other. At the same time, the water-loving heads happily face the outside world and the inside of the cell. And just like that, poof, you get a two-layered sheet, a bilayer. That's the basic fabric of our membrane. Okay, so that brings up a really important question. If this wall is, fluid, what's to stop it from freezing solid in the dead of winter or melting into a useless puddle during a heat wave? The cell absolutely has to maintain the right consistency to work properly. And yeah, it's got a pretty clever trick up its sleeve for that.
The whole secret is in the shape of those fatty acid tails. See, the tails made of saturated fats are perfectly straight. This means they can pack together super tightly, almost like a neat stack of pencils. That makes the membrane more solid. But the unsaturated fat tails, they have these kinks in them, these bends. And those kinks make it impossible for them to pack together tightly. It's more like a jumble of bent straws with lots of space in between. That's what keeps the membrane nice and fluid, especially when it gets cold.
And check this out. This is a perfect real-world example of why this matters. Think about a fish swimming around in icy cold water. Its body will actually start producing more of those phospholipids with the kinky, unsaturated tails. Why? To stop its cell membranes from basically turning into cold, hard butter. It's an incredible adaptation that allows all the cell's machinery to keep moving. For that fish, it's literally a matter of life and death.
All right, let's move on. We've talked about the wall itself, but now let's talk about the really interesting stuff, the gates, guards, and workers. You see, that lipid bilayer gives the city its border, its structure. But all the real action, that's thanks to the proteins floating around in it. These things aren't just bricks. They're the gatekeepers, the security guards, the factory workers. They're everything. This is why we call it the fluid mosaic model. It makes perfect sense when you look at it. The fluid part is that sea of lipids, but the mosaic part, that's all these different pieces. You've got the lipids, cholesterol wedged in there, and this huge variety of proteins just drifting around. It's not static at all. It's a super busy, constantly shifting environment. So, we can basically split these protein workers into two big groups. First, you have the integral proteins. These are the true insiders. They're embedded right into the oily middle of the membrane. A lot of them go all the way through, from one side to the other. Then you have the peripheral proteins. Think of them as associates or consultants. They just hang out on the surface, either on the inside or the outside, loosely attached.
And what do these proteins actually do? Well, pretty much everything.
Some of them are for transport, they're the gates and tunnels of the city. Others are for cell signaling, they're like the communication towers, receiving messages. Some have enzymatic activity, acting like little on-site factories. And others are for cell adhesion. They're literally the Velcro and anchors that hold tissues together. They're incredibly versatile.
Okay, next up, border control. We've seen the wall, we've met the workers. Now what are the rules for getting in and out of Cell City? Because this border is what we call selectively permeable. That's just a fancy way of saying it's a very picky bouncer. This image gives us a fantastic overview. You can see there isn't just one way across. Some small stuff can just sneak right through the lipids themselves. But other things, they need an escort, a protein to help them. And then there are the VIPs that require the cell to roll out the red carpet and spend some serious energy to get them across.
This chart is your cheat sheet. It lays it all out perfectly. Basically, you've got two main options: passive transport, which is free, no energy cost, and active transport, which the cell has to pay for. Passive transport is all about going down the gradient. Think of it like rolling downhill, from where there's a lot of something to where there's less. Simple diffusion is when stuff rolls downhill on its own. Facilitated diffusion is when it still rolls downhill but needs a protein to open the gate. And then there's active transport. This is the hard work. This is using energy, ATP, to push something uphill against its gradient.
Now, for that facilitated diffusion, the one that needs a helper, there are two kinds of protein helpers. You've got channel proteins, which are exactly what they sound like. They're just an open tunnel. If you're the right molecule, you can just zip right through. Then you have carrier proteins. These are much more like a revolving door. They grab a molecule on one side, physically change their shape, and then spit it out on the other side. Grab, flip, release.
So what about the really, really big stuff? I'm talking huge cargo, like entire proteins. For that, the cell has a bulk transport system. To bring things in, it uses endocytosis. The membrane literally reaches out, engulfs the material, and pinches off a little bubble called a vesicle inside the cell. It's like the cell is eating. And to ship things out, it does the reverse, exocytosis. A vesicle from inside moves to the edge, merges with the membrane, and dumps its contents outside, kind of like spitting it out.
Okay, we're in the home stretch now. Let's move into our final section, a little final exam prep. We're going to wrap up our tour with a quick review, but first, there's one last critical piece of the membrane we have to talk about. This piece is all about how Cell City identifies itself and interacts with its neighbors.
So sticking out from the outer surface of our city wall are all these little sugary chains, these carbohydrates. When they're attached to proteins and lipids, they form something called the glycocalyx. And the best way to think of these? They are the cell's molecular ID badges. Every cell type has a unique badge. And get this, they're even unique to you as an individual.
And why does this matter so much? Well, this is exactly how your immune system tells the difference between your own cells, what we call self, and a foreign invader like a bacteria or virus, which is non-self. Your immune cells are constantly on patrol, checking these ID badges. If they find a cell with the wrong ID or no ID, they know to attack. It's a critical security system.
All right, pop quiz time. Let's see if you've got this. Let's go back to our fish. Suppose we take that cold water fish and move it into a nice warm tropical aquarium. Now, its membranes are in danger of getting too runny, too fluid. So to make them more stable, what kind of fatty acids does its body need to start producing more of?
The answer? Saturated fatty acids. That's right. Because in that warm water, the fish needs to make its membranes less fluid, more stable. By making more of those straight, saturated tails, the phospholipids compact together more tightly, which thickens up the membrane and gives it the stability it needs to work in the heat.
And that brings us to one last thought to leave you with. We call it the fluid mosaic model. We've spent a lot of time on the fluid part, that sea of lipids. But I want you to think about what really makes it a mosaic. Is it the lipids? Or is it all those different proteins scattered throughout? It's the proteins, right? They're the colorful tiles that give the membrane all its specific, amazing functions. They make the border of every cell a unique, dynamic gateway to the world. Thanks for coming on the tour today.